So today we will see some things about shear-wave splitting, and we will analyze some waveforms with the Pytheas software to see the anisotropic effect on the recorded waveforms. Now, it's very important to talk a little bit. I know this is a hands-on session, but we need to talk a little bit about what shear-wave splitting is. So, very briefly, what's shear-wave splitting? It's a property of the propagation medium, which in our case is the upper crust. And shear-wave, it's the phenomenon when a shear wave splits into two new, let's say, waves with orthogonal polarizations. To understand better, you can see in this picture that you can see my pointer, the mouse. Okay,
yes.
Thank you. So you can see that we have an initial shear wave here in an isotropic medium. It enters into the anisotropic medium and it splits into two different waves which travel with different velocities. So you can see here in this, let's say, cube, that there are two waves, one here, which are orthogonally polarized. When they exit the anisotropic medium, they keep this this split. So we have two new waves that are recorded in the station, and what we see at the seismological station is this phenomenon right here to the right. These are recordings from two horizontal channels, and they are synchronized, so all these waveforms are at the same time, and you see that at one waveform, the shear wave arrives earlier than in the other. So this is splitting. We have two waves. Some key concepts to understand what we're going to do. So the first one is the polarization direction of the fast shear wave, which we will call from now on phi. This is the polarization direction of the fast of this wave. You see here to the left, this direction. And another very important property of shear-wave splitting is the time delay, TD, which is the difference between the arrival times of the fast and the slowest wave. Now, shear-wave splitting, which is a part of seismic anisotropy, is very well studied in the Western Gulf of Corinth, and CRL has helped a lot in that, because we have a very, very dense network there with a lot of earthquakes. So the amount of data that we have in our disposal is massive. So some other key concepts, it's the fluid field microcracks in the upper crust that are related to shear-wave splitting. This is what causes, or at least we assume that causes the shear-wave splitting in the upper crust of the Gulf of Corinth. And this can function as a proxy for stress variations, which in turn can be related to forecasting of earthquakes and volcanic events. Now, I've talked very briefly about all that. I'll give you some literature references next, if you are interested in reading more. So, the software we're going to use today is called Pytheas. It's software we have developed in the seismological laboratory of the University of Athens. It was released last year and contains manual, semi, and fully automatic splitting analysis methods. There's also a graphical interface for easier use, and it can be used either for research purposes or, as we will see today, for educational purposes. And it is built, of course, with CRL data, which means that all the seismological data that we used for developing, for testing, and for whatever, they are from the CRL network. So here, this very short presentation will be uploaded, so you can do some further reading if you're interested. And here are some references for studies that have been conducted in the Western Gulf of Corinth and concern shear-wave splitting. So that was a very, very brief introduction. Give me a moment to swap to the actual software. Okay. Okay, so if you have installed per the instructions that were provided for this exercise, the Pytheas software and all the prerequisites, you should be able to start the program right now and see this initial image. Now, according to the exercise, what we'll do today is to use some CRL data, try to determine the polarization direction, the time delay, and then validate our results and see whether we have done a good job or not. So to start, you can open the catalog through the toolbar menu. You can open the catalog, and then you need to provide 3 different paths. The first one concerns the data that you will use, which means the waveforms, which are either in the SAC or MC formats. Then a catalog file. We use an XML file, which is used internationally nowadays. And then we can specify, we can specify the database file. This is where our results will be stored and archived. So you can either browse to it through this menu, or you can simply do what I did. So you can just copy and paste the path to the catalog and then change the extension of the file. So just like that, and then change the extension. All these that I'm talking about are detailed in the given exercise file. So you can start then the software, like so. And after it reads the catalog and it finds all the waveforms, you can see the very first data. And now I'm going to cheat a little bit, and I'm going straight to the good example, to the good waveforms. But you can, after I show you how we do the analysis, you can do it for all the data. There are 4 events provided with Pytheas that you can analyze and play around with the software. So we opened the first, let's say, event station pair. This is a station that is located in the western Gulf of Corinth. It's called Mala, and it is a borehole station that belongs, of course, to the CRL network, and we have been using it for many years. So the first step after you open the waveforms is to apply a filter. We need to clear up all this noise a little bit to be able to perform a CR-wave splitting measurement, because we need the very impulsive arrivals of CR waves. So this is the initial image of the waveforms, and I just use the shortcut Control and F, which applies, I just did it, which applies a band pass filter between 1 and 20 Hertz. Now, with the wheel and this, while holding the Shift key and using the wheel, you can manipulate the x-axis, the time axis, and you can either zoom in, like I do now, or zoom out in the waveform. You can use just the wheel without any other key to change the y-axis, meaning the amplitude of the waveform. And so you can play with the wheel either with Shift or without Shift to get the best view of the CR waves as it suits you. So I'm going to zoom in a little bit more. Okay, so now it's time to talk about what we're seeing right here. The first diagram, the first subplot, is the vertical component of the seismogram. The second one is the north component, and the third one is the east channel. You can see these are marked to the left of the y-axis. Now, what we see down here is what we call the polarogram. The polarogram is just a synthesis of the amplitudes of the two horizontal waveforms. In other words, this diagram, its vector, its line, shows us how a ground particle would have moved if we were there to see it. And in the last row of figures, right here, you can see what we call the hodograms, the particle motion diagrams. So these are for different time intervals that you can see to the top left of each diagram. But here you can see even better the continuous movement of the particle motion. So why do we use these diagrams? We use these diagrams to determine in the first place what we call phi, the polarization direction that we talked about earlier. So the first step, after we clear up the waveform with Control F, and after we have zoomed in for a better view of the CR waves, is to pick the arrival of the CR waves, of the fast CR wave. So you see here, there is an arrival of CR waves here, I can identify, and one other here. I don't want this one, I want this one, because we want the polarization direction of the fast CR wave. So to pick the arrival, this is, by the way, this is an already picked arrival from the catalog, so there is no measurement associated with it yet. So to pick the fast CR wave, you can use Control and left click. And as I will do it now, you will see that the line moved, which means that I picked the S arrival. Now, when you pick the CR wave arrival, at the same time here to the top left, you will see that the phi value changes. This is because the program automatically determines the angle, the angle of the vector. So for example, if I pick another vector, it's going to change. It's going to be 56. Obviously, we don't want that, and we want this direction. So this is the arrival of the fast CR wave. Now, this is the first step. The second step is to determine the time delay, as we talked about earlier. To do that, after we have picked the arrival of the fast CR wave, we can use Control and 2 to go to the second stage of the measurement. I'll do this one more time. So this is the initial stage, and with Control and 2, we go to the second stage of the measurement. Now, at this stage, what we have done is we have rotated the horizontal seismograms according to phi. So these are the seismograms that we would have recorded if the north channel was oriented according to the polarization direction. Now, we do this because in this case, when they're rotated, we can see the time difference more clearly. So as we are at this stage, at the second stage, we use the arrow keys to move the bottom waveform, the slow waveform. So for example, if I press left, you will see that it slowly moves because the software moves temporarily the bottom waveform by one step. And the steps are very, very small. In our case, each step that the waveform moves is 10 milliseconds. So what I'm trying to do is I'm trying to match the arrival of the CR wave in this component with this component. So I'm going to start again from there we go. This is the initial stage where there is no time delay measured. Now we want to move the bottom waveform, and I move it with the left arrow key until I see that the CR waves match, and I am happy. There we are. Okay, so how do I see that the CR wave match? To do that, you can find a trough or a high amplitude, let's say, part of the waveform and try to match them. In this case, I'm trying to match this trough with this peak. And I see that they do match well. I'll always zoom in, zoom out, with changes in amplitude, whatever suits you better to identify CR waves in the waveform. So I believe that I did a good job here by matching those two, this trough and this peak. And also note that while I move this waveform, the bottom waveform, the particle motion diagrams, the polarigram changes as well. What you want to achieve at this stage is ideally a parallel polarigram. So these vectors that correspond to the CR waves should be completely parallel, or at least as most parallel as you can. There's always noise, there are always factors that don't let you do that. So in this case, I believe I did a quite good job. You can see they're almost parallel. And we can proceed to the validation stage with control and 3. What this does is that it rotates the horizontal waveforms back to the north and east system. But this time we have removed the effect of anisotropy. So these are the waveforms that we would have taken if there was no anisotropy in the propagation medium. And the goal here again is to have these vectors as much parallel as you can. And as you see here, these are parallel between them. And now I can see that the two waves arrive at the same time. So I'm going back to the first stage with control and 1. You can see that there is one wave here and one wave here. There is some evident time difference between the arrivals of the CR waves. Now I go to the corrected stage with control and 3, and you can see that, yeah, I did quite a good job, apparently, because you can see that the CR waves arrive at the same time. Now, the last step in this process is to press Control and X, and you can set a grade, A being the best and E being the worst. I'm gonna set A because it was a perfect example. And this is how you've taken a CR wave splitting measurement. As you can see, well, this is a very good example, but it is, especially with experience, it can go really, really fast. So this result now is automatically stored to the database. And you have the following options. Here in the database menu, you can either export, which means that you can export all your results into a CSV file to use them in Excel, or you can export figure, which generates a summary figure of your measurement that you want to display, for example, in a paper or your presentation or whatever. Now, how much time do we have? I think we're still...
We have 10 minutes.
10 minutes, okay. I don't know if before I go to the next, if there are any questions. Let me see the chat. Okay. So I'm going to summarize the process really fast. And this is, okay, let's go to a different measurement. What else you can do with this software? this is not for analyzing just one pair of station events. So there is, if you press Shift and E, there is, you can see the whole catalog that you have loaded into the program. So for example, I'm going back to the first event. And then if you press Shift and S, you can see all the available waveforms that you can analyze. So this program can be used for mass analyzing data for CR-wave splitting. And of course, there are many, many more functions for whoever is interested. For example, automatic analysis, semi-automatic analysis, which are beyond the scope. So to summarize, if you want to take a measurement, the first thing you do is you apply a filter to clear up the waveforms. Then, then you pick the arrival of the fast waves, of the fast CR wave. Then you go to the rotated stage where you measure the time delay with the arrow keys, which measuring the time delay means that you move the bottom waveform. And then you can validate your results in the third stage by seeing that the CR wave in both components have arrived at the same time. So this is a very brief introduction, CR wave splitting and Pytheas. And I can see that in the exercise we have provided, there are some questions that you can answer. For example, you can measure, you can take a measurement, and what is the polarization direction? What is the time delay? Just measure. And of course, for everybody who is interested in other CR wave splitting, or using the program in general, we are both available, me and Professor Kaviris, for any questions or any other issues that you may have.